Okay, cool. So thank you all for coming. So we're going to have a joint, partially virtual 1W-MINDS seminar. Partially there are people here at UCSD. So hybrid. We'll see how that works. Anyways, so today we're very happy to have Keaton Hamm here to give a talk. Keaton's at University of Texas at Arlington. And a good colleague, and does some really cool work on a lot of different areas. But today we'll be talking about tensor decomposition. So go ahead.
All right, thanks, Alex. And so in the hybrid format, I may be pointing to this. If there's any issue with understanding that from the online audience, do let me know. So thanks to the organizers for the invitation. It's great to be here in San Diego and online. And so I am going to talk today about low-rank tensor decompositions. So we'll get into that shortly. So first of all, this is joint work with a variety of really cool people. So Longshu is one of the organizers here, of course, and obligatory thanks to the sponsors, NSF and the Army. So here's my sort of the model I'm going to start with for data matrices or tensors. So I've drawn here the matrix representation. I'm going to assume that I observe some data matrix or tensor, but it's actually some low rank matrix or low rank tensor plus some noise. And this is a really broad model. So in various cases, we might assume that the noise is small magnitude, for instance, or coming from some noise distribution, such as random Gaussian, or it could be sparse noise of arbitrary magnitude, something like that. So this covers a variety of different models. I'll go into a little bit of detail in one or two instances later on, but this is going to be our starting point. And sort of a pictorial overview of the theme of my talk is that I want to build algorithms and low-rank matrix and tensor decompositions that work on the principle that because of the low-rank structure underlying the data, I don't need to observe all of the data tensor. And what I'm going to try to do is try to get away with only observing some fibers of the tensor. So here on the left in the matrix case, I'm going to assume that I only observe a few columns and a few rows of the data matrix. And in the tensor setting, we'll see there are a couple of natural analogs of this idea. So I'm going to assume in this case that I observe sort of some fibers in any direction that are connected to some sort of core subtensor that I observe. The indices don't have to be continuous here. That's merely for aesthetic reasons. And then over here, I'm going to assume that I observe some core subtensor and then some fibers along every mode. So I'm only showing one mode of fibers here. Okay, so I'll describe those decompositions more explicitly later on, but that's the idea. So if I want to denoise my noisy observations, I only want to do it on some small set of fibers, and then I'll use the decomposition approach to get back my full low-rank tensor. So I'm going to start from the matrix case and then use it to motivate the tensor case. So this is a decomposition for low-rank matrices called a CUR decomposition. It has a long history that in some form or other can kind of be traced back even to Penrose's papers on defining pseudo-inverses and things like that. And essentially, I give the theorem as folklore here because it's pretty hard to trace like where it actually would have come from, but it has sort of a long history, and I'll give a few pointers to that in a minute. So the theorem says, suppose I have a matrix A here, and suppose I extract some columns, which are these red bars here, subtract some rows, which are in blue, and then the purple entries, of course, are the intersection or the overlap between those selected columns and rows. And the theorem says that if I chose columns and rows judiciously enough such that the rank of that small purple matrix U is the rank of the full matrix A, then I get this exact decomposition. A is the product of columns, the Moore-Penrose pseudo-inverse of U, that middle matrix, times the rows. So here is sort of the picture of what the decomposition looks like based on how I did that before. So of course, the question in a practical setting would be, how do I sample? How do I choose those columns and rows such that I can do this, right? And we'll talk a little bit about that, although that's not going to be the main focus of my talk today, right? So the nice thing about this is there's a few nice things. One is that I'm representing my matrix A by some small numbers of actual columns and actual rows. And that means that I actually know something about what those columns and rows are in a certain data domain. So if I'm dealing with like patient data where I have patients, maybe as rows and gene expression levels as columns or something like that, if I do an SVD, then I'm representing them in an orthogonal basis, which is great, and it gives me a lot of information about variance and so on. But I sort of immediately lose some amount of interpretability because the singular vectors are just linear combinations of the actual features or the patients, if that's what I care about. And so here I have a basis representation in terms of actual features, right? So there's an interpretability aspect of here that is preserved by CUR decompositions in a way that's not with every other type of decomposition, okay? And so since this is a math talk, I wanted to give a really short proof because I like the fact that this is provable by very basic linear algebra techniques. So let's do the case when I choose the same number, I choose rank many columns and rank many rows. So U is invertible by assumption. And by the assumption then, the columns of C form a basis for the column space of A. So I exactly captured the column space. And therefore, so I can write A as some product of C times some unknown matrix of basis coefficients X. Now I suppose I have some row selection matrix P sub R that's giving me the selection of rows when I hit A on the left-hand side with it. And then all you really have to observe is that, so the forward directions of all these are obvious, but because going from this representation of A as C times X, any solution here has to also be a solution to the right-hand side here, which is the rows. I hit both sides of this equation with that row selection matrix, but because I'm preserving the rank by selecting those given rows, any solution to the right-hand side here is a solution to the left-hand side as well. And so, and here, this is just, the last one is just by definition, and it's obvious what a solution to the last equation is, which is cut off by my window bar here. Okay, that's okay. So the solution here is U inverse X or U inverse R, right? So then A is C times U inverse R. So super simple proof. And it's the generalization to the pseudo inverse case is pretty straightforward. You just kind of have to iterate this argument again, but it's really not so bad. Okay. Oh, somehow I got off on my, that's what happened. Okay. All right, so here's the sort of the main ideas in CUR decompositions, right? I'm using submatrices to reconstruct, or in the general case, approximate my data tensor or matrix. I want to choose good columns and rows or good fibers that represent the matrix well. So in the matrix case, I want to capture the column space, capture the row space exactly, or within some small error. And then reasons why I would care about this. Interpretability is one that I already discussed. In machine learning, you can use these techniques to approximate kernel matrices, especially for kernels where maybe evaluating a single entry of the kernel could be costly. So in optimal transport, which is another part of my research, evaluating one entry of an optimal transport distance matrix or Wasserstein distance matrix is computationally expensive. And so you can use this idea to only compute a few columns of your like kernel matrix. A lot of the theoretical computer science community has used this to make a fast approximation to the SVD, and a lot of the work there dealt with how well do you approximate the truncated SVD error by oversampling columns. I'll talk about some sort of robust low-rank matrix approximation methods later on. And then one other reason that this can be useful, as I mentioned, is it does preserve some structure. So if my original data matrix or tensor is sparse, the columns and rows or fibers that I sample will also be sparse, which is blown out if you do the SVD, for instance. Okay. A few applications, I won't talk about all of these today. I've applied these to the subspace clustering problem, which has applications in like motion segmentation, facial recognition, even some in cryo-electron microscopy. You can use it as a way of sketching massive data matrices, especially ones that you can't store in core memory. And then today I'll talk briefly about some image processing applications. Okay. So here are just some themes in the area. The literature at this point is now fairly mature. Some of the key takeaways from a lot of research by a lot of people over the decades is that if I typically want to mildly oversample columns. So if I want to approximate the SVD of a matrix of order K, then often I will have to have some oversampling factor here where I sample K plus something that's hopefully small. And it turns out that in many instances you can quantify this, and it does a really good job of recovering the SVD. It's good for approximately low rank matrices. Of course, if I have a truly full rank matrix, this is not going to give you a very good approximation, but in that case, other techniques will suffer as well. And there's been some work on sort of creating random hybrid algorithms where you sample some columns and rows randomly at first according to some distribution, and then you refine that by some either you call columns that are redundant or you have some extra deterministic sampling step. So again, many ways to sample here. And then one that will come up at the end of the talk is that if I have a matrix that has small incoherence of the columns and rows, which I'll define later, then uniform sampling of columns and rows is known to give me a good set of columns. Like it very well approximates the column space. Okay, so again, because the literature is broad, I want to give some pointers to how you might see it in the literature. So if I just do sort of a one-sided thing where I just have columns times some unknown matrix, that's called an interpolative decomposition. So CUR can be viewed as a two-sided interpolative decomposition. In the form where I have columns times something times rows, that's how it's often referred to, especially in theoretical CS. Those are called CUR decompositions. We'll talk about a couple different ways to actually choose that middle matrix in a second. In some of the areas, it's called cross approximation, or this is sort of more or less the same thing with some variations. It's been called skeleton or pseudo-skeleton decompositions. And when the matrix is symmetric, positive, semi-definite, aka a kernel matrix in machine learning, then it's called the Nystrom method. Okay. And then there's some recent generalizations of this, so generalized CUR and metafactorization by a few different authors. So I want to just briefly mention that when I go to form this product, there are sort of, in some sense, two natural ways to choose that middle matrix. So I have columns and rows on one side, and then I have something in between. And one of them is what I showed before. I just take that small submatrix Aij and take its pseudo-inverse. So that's what I showed in the folklore theorem. And so I say natural because it gives you that exact decomposition, provably. The other natural one, for two reasons, is to take the middle matrix to be this seemingly complicated thing where I have the pseudo-inverse of the column and row submatrices on the left or right of A. The reason this is natural is then my approximation looks like this. And that's sort of natural for two reasons. One, what I'm actually doing is this C times its pseudo-inverse is the orthogonal projection operator onto the column space spanned by C. And so I'm saying, well, I'll take my matrix A, project it onto the span of the few columns I chose. So if I did a good job, then that's going to be a good projection. And then I do the same thing on the right-hand side. I project the rows onto the row space of the rows that I chose in R. And again, if I did a good job, then that's going to be exact or very good approximation. And the other is you can prove that in the Frobenius norm, this is the minimizer for fixed C and fixed R of the Frobenius norm of this difference. Okay, so those are kind of two reasons why this is very natural to consider. From an algorithmic standpoint, the first one is better because my computation cost really boils down to taking a pseudo-inverse of U, which is a very small matrix. So that is efficient computationally. And even doing this matrix product isn't really a big deal. Forming these orthogonal projections and then needing the entire data matrix A in the second case is not really ideal. That's not going to help me, especially if I can't store A in memory. Okay, so there's some trade-offs there. Theory is better for the second one. Practice is better for the first one. So I want to just highlight how these are connected in a certain way. So suppose, never mind how I sample columns and rows for the moment, but just assume that I do it in such a way that the rank of that small matrix U is the rank of A. So these statements are all equivalent to that. So I showed you already the proof 1 implies 2. It turns out that in this case, that these two ways of decomposing A in 2 and 3 are equivalent. And that's not too hard to show. The fourth one is kind of interesting. So as a reminder, pseudo-inverses don't split over products like inverses do. So it's typically not the case, except for under special circumstances that are characterized that AB pseudo-inverse is B pseudo-inverse, A pseudo-inverse. But in this special case where I have this exact decomposition of A and 2, then I can sort of take pseudo-inverse of A as I would like to, and it happens to be true. Okay, and those turn out to be equivalent. And the fifth one is one that we're able to exploit in algorithms. We really, as long as we choose columns and rows such that those ranks preserve the rank of the original matrix A, then that's equivalent to having these exact decompositions. So in a way that helps us build algorithms where we independently sample columns and rows, and then we have sort of guarantees that enable us to stitch those together to get a good approximation to the matrix. Now, one comment here in the non-exact case, right, when A is approximately low rank or something of that nature, there are sort of multiple ways that one could choose to enforce the rank. So I'll just mention two here, and I won't talk too much about it, but one is just to take that middle matrix U, do its truncated SVD of order K, and then take pseudo-inverse. This can sort of magnify some noise in some applications, but it is a really simple and cheap way to do it. The other would be to form the whole product, C U pseudo-inverse R, and then rank truncate it. So for symmetric matrices, this is provably better than the other one I just said in the nuclear norm, but not necessarily the other norms. So there's sort of some advantages and disadvantages to various approaches. So that's kind of where I'll leave that. Okay, so I want to now move on to tensor decompositions. And so the thing is, when you want to define tensor decompositions based on this matrix idea, at least as far as our experience goes, you kind of have to have a tensor decomposition type in mind. So either you want something like a Tucker decomposition or like a T product type decomposition or a CP decomposition. And so often the way you're going to do that decomposition is going to influence the types of algorithms that you create and even what you mean by a tensor CUR decomposition. And currently, I don't know that there's a way around that. In a way, I think we might just be stuck with that idea, but so I'm going to highlight a Tucker type approach today, but I'll talk a little bit about T products. So my tensor, the dimensions will be D1 through Dn, so that's an n-mode tensor. This is an illustration that I took from this nice survey paper by Zer and others. And so here I'm just showing you, so the different modes of my tensors. So for 3 tensors, my first set of modes is going to be like the rows. The second set of modes is going to be the columns, and the third mode is going to be the like spatial like z-axis. And so here, these are the mode 3 fibers going back, mode 1 fibers going up. So then the mode 2 fibers would be going across like this. And then we'll have some occasion to talk about slices of different modes. So these illustrated are the mode 3 slices or frontal slices, depending on your terminology. Okay, so that's just a brief illustration to have in mind. Obviously, you can choose different numbers for the modes. It doesn't matter. So just pick your favorite convention and go from there. And because we're going to talk about Tucker type decompositions, I'm going to need to reference unfolding of this tensor along a certain mode. And really, so here's unfolding the mode 1 fibers. So I have all these mode 1 fibers color coded, and I start here at the first index of the first mode, and I go back and then back, and I stack those all as a short fat matrix. Okay, and I'm always, no matter what mode I'm going to do it along, I am going to stack it in this way so that the fibers end up vertically. Okay. And so in general, if I have the ith mode unfolding of T, it's going to be a matrix of size di by the product of the other dimensions. Okay, so it's always going to be this short, like super long matrix. And then the mode-wise product briefly. So if I want to multiply a tensor along its ith mode by a matrix, the matrix has to have the second dimension equal to di, and the first dimension is whatever it is. And so I take the ith unfolding of the tensor, multiply on the left by the matrix, so it eats that dimension di and changes it to t, whatever the size of the matrix is, and then I just fold that back into a tensor. So that's one way to view that operation. And so the rank is not a uniquely defined notion for tensors. And so when I say low rank tensor decomposition today, I'm going to be considering primarily multilinear rank or Tucker rank. And that is a tuple of n different ranks where each Ri is the rank of the ith unfolding of the tensor. So in a way, this is, you're viewing your tensor as a bunch of matrices by unfolding, and you're looking at the rank of those unfolded matrices. Okay. And the Tucker type decompositions that we're going to be considering are of this form. So I have some core tensor S that in general, Tucker doesn't have to be like a subtensor of T, but for me, it will be. And then a bunch of mode-wise products, with a bunch of factor matrices. So in like higher order SVD, often you constrain these to be orthogonal matrices. For us, we will not make that constraint. We will have it be in terms of some subtensors. Okay. So then how do I form a Tucker type tensor CUR decomposition? So we know two primary ways to do this. And so here you have on the left, and again, I'm going to choose the indices that I sample to be in a continuous set just to make the visualization easier. So I'm going to assume that I have sampled this rectangular subtensor that I'll call R. So I have everything in that. And then I take that and I extrude it out along all different modes. Okay, and so I take all the fibers in every direction that pass through that little core subtensor. Okay, and then basically the little blocks, the red, green, and yellow blocks here are going to form my factor matrices in the Tucker decomposition. Okay, so from here to here, R is the little dashed rectangle, and then the factor matrices basically are coming from doing something like a matrix CUR decomposition on each unfolding of the tensor. And so what I do is if I'm looking at the green one, I look at, so C1 is basically that whole green subtensor unfolded along the first mode. The equivalent of the U pseudo inverse from the matrix case is I take the unfolding, but I restrict it to the indices that come from the box along that mode, right? And so that really is the analog of my matrix CUR decomposition. And then I just do that for all of these different blocks and get this decomposition. So we call this Chidori, and this was we got the name from Dustin Mixon. Chidori is it looks exactly like this. It's like a Japanese joint that's made out of wood. Actually, the process of carving it's super cool. Like I watched a YouTube video last night about it, and it's like this crazy, really intricate process of doing it, but it's like super strong. So anyway, so that's one type. Interestingly, it turns out, and this is true even in the matrix case, I can do it a different way where again, I call R this little box in the middle, but then I sample a bunch of fibers along every mode. So here I'm only showing the mode 2 fibers, and they may or may not actually pass through that dashed box R. So like in the matrix case, I choose some columns and rows, but instead of choosing their overlap, I kind of just choose some different indices for the middle matrix. And it turns out that actually still works, which is kind of interesting. And so in a way, you can use this to have a little bit less structured of a decomposition. And so here, the C1 or C2 in this case would be, I take all these fibers and I take them as a matrix, and that's my C1. And then or C2 in this case, the U2 pseudo inverse is I take all the red pieces, which is where I overlap with the indices of this core subtensor. And then those are a matrix, I take their pseudo inverse, right? So that's how I form my factor matrices. So it's a little bit hard to visualize, but hopefully just picture stacking these and then stacking the red ones together, and all the color goes together. All right, so these are two ways to do a tensor CUR decomposition when you're looking at a Tucker factorization, right? And I'm going to state briefly the equivalent of the characterization theorem I had for matrices. In the absolute most general form that I know it to be true, just to sort of show you what is true in this case. So I can actually assume that my tensor has entries in some arbitrary field, and I have its multilinear rank that I know, and you can ignore the index sets here. Just picture this picture here. So I'm using this Chidori decomposition here, and what I need is those little submatrices UI have to match the ith piece of the multilinear rank for all I. And then I get sort of the equivalent thing I had before of I have that core subtensor R, I have these Chidori factors. And the interesting thing is here, I don't have to have pseudo inverse. You can do it for any generalized inverse. So that's one that only satisfies like the first Moore-Penrose identity and may not satisfy the others. And it turns out that if I get a decomposition for one generalized inverse, I get them for all. So it really doesn't actually doesn't matter for an exact decomposition. And then the fourth one is that the multilinear rank of the core subtensor is the same as the full data tensor. And so yeah, I won't dwell too much on that. For T products, let me scroll down so you can see footnote here. So I won't really rigorously define a T product here, but essentially it's it's defined for third order tensors. So people often use it for either images or maybe like time series data. And it's defined by taking the circulant Fourier transform along the third mode of the tensors, multiplying them in Fourier land and doing an inverse Fourier transform. But there you're taking just slices like this and then the fibers in the third mode to form the products. And just briefly, the exact same analog of the theorem I showed for matrices holds for T products. Okay, so now I want to get into sort of analyzing what does this Tucker type decomposition using only these fibers give me. So this is a more technical theorem that I'll simplify in the next slide. But what I want to understand is, so suppose I have now my data tensor that I observe, which is, we'll call it T tilde, which is some low multilinear rank tensor T contaminated with some noise tensor E. Okay. Under some technical conditions, so I need some sort of gap in between the smallest singular value of the subtensor that I chose and the norm of the noise tensor on really on that piece that was that rectangular block with dashed lines, that small core subtensor. So under that condition, essentially what governs my error are, so really all I want you to take away from this slide is I have some norms of the noise tensor may be restricted to some indices. So here I have one piece that's just the noise tensor on that small rectangular piece. Here I have some slices of the noise tensor. And then the other thing that mainly governs the error is norms of pseudo inverses of submatrices of the left singular vectors. So in the matrix case, I have my low rank matrix, I have its compact SVD, and if I sample some columns of the matrix, then I sample the corresponding rows of the left singular vectors, take a pseudo inverse, and whatever the norm of that thing is, that's really what's going to govern my error. And so there has been some analysis that I'll point to a little bit in the next slide of how large can those be. Okay. So really that's all it is. So then in the practical case, so here's just one sample of how you could use a bound like that. So I'm going to, in order to largely simplify the bounds, I'm going to make some simplifying assumptions here just so it's not as messy. So my tensor is going to be n mode, but all the dimensions are the same just for clarity of the bound. And I'm going to assume that the multilinear rank is a constant tuple. So all the ranks are the same along any unfolding. Okay, and so suppose my noise is IID Gaussian with standard deviation sigma. Okay, and then essentially what this theorem says is, so I want to understand what happens if I uniformly randomly sample indices along each mode, and then do the CUR reconstruction. Okay, and so I'm gonna for simplicity do the Chidori CUR of my noisy data tensor, and what you find is actually, so you need to sample incoherence times rank times log of the dimension fibers along every mode. So I'll define the matrix incoherence explicitly in a couple of slides. Loosely for now, it's you want your singular vectors of a matrix to be closer to a discrete Fourier transform matrix, so kind of spread out as opposed to the identity matrix, which is sparse. For a tensor, the tensor incoherence definition that we use here is simply the maximum of the matrix incoherence of all the unfoldings. Okay? So feasibly different ways to define that, but that's how we did it. So really not many fibers if it's truly low rank, right? Log of the dimension up to that rank factor. And then under some technical assumptions on kind of the smallest singular value of the low rank tensor piece, what you get is the error of the Chidori CUR decomposition is upper bounded by, and really the key features of this bound is this is order of constant to the n, where n is the number of modes, not the dimension. Okay, and then here I have like a tensor condition number. So by sigma max of the tensor, I mean the largest singular value of any of the unfoldings. So I just take the maximum. Same for the minimum. I take all the unfoldings, look at all the singular values, look at the minimum non-zero one. Okay, and then this is again just dependent on the number of modes. L is the number of fibers I sampled, so that's something on the order of R log D to some fixed power that's close to 1. I have this square root of a logarithmic piece. Again, it's just logarithmic in the dimension if you piece all this together. And then this looks kind of bad because I have dimension to the n over 2 times sigma. Really, this is just the expected noise of the random Gaussian noise tensor. Okay, so whatever your noise is, that's here. So effectively what you're saying is the bound is only contains pieces that are exponential in the number of modes, not the dimension, and then up to this condition number of the noise tensor. Yeah.
So, all right, when I think about, bounds like low rank matrix plus noise on matrices.
Yeah.
I generally think about, all right, take an arbitrary like signal, which in this case would be your low rank matrix. Its eigenvalues are not all going to be just constant. There's going to be some rate of decay of the eigenvalues,
right,
just due to random chance.
Right.
But that rate of decay is pretty slow for matrices, which means you can add a lot of noise.
Right.
Right. In tensors, I have no feel for how fast, if you pick a randomly low rank tensor,
yeah,
how fast the singular values decay.
Right.
Do you have any statement about that? I know that this is a little bit tangential, but I'm trying to get a feel for whether the amount of noise you're allowed to add in a Gaussian is machine precision or small.
Yeah. So maybe, I don't know if the online audience could hear it. I'll very briefly summarize the question. What does the spectral decay of a low rank tensor look like? Is it fast? Is it flat? Yeah, I think I don't completely know the answer. I do think because you're dealing with all of these different mode unfoldings, I think the amount of sort of Gaussian noise that you can add to a low rank tensor is probably significantly less than you could do to a matrix. But I don't have a precise proof of that or anything, but that would be my feeling. But yeah, great question. And this is with some probability. Right. Okay. So that's kind of the main result that theoretical result that I wanted to mention today. And so in my last few minutes, I'll talk about an application and then maybe have time to talk briefly about how to use these ideas for robust PCA. So here's just a really kind of simple experiment. These are some RGB images shown, but coming from a hyperspectral image data set or 3 different hyperspectral data image sets. So you have a couple of city scenes, and then on the bottom row, you have sort of a plant scene. So what you're seeing is on the left-hand side, you see the original image, and then on the next 3 columns are different compressed approximations of this image. So on the very right-hand side is the higher order SVD of a fixed rank, and then in the middle 2 are the fiber and Chidori CUR. You're not going to see much difference between the fiber and Chidori variants here. In later slides, there might be a little more difference. Really the upshot is they form decent approximations with still sampling about, I think we maybe sampled 5 times log of the dimension or something like this. I actually have the numbers on the next slide. Interestingly, one really small thing I'll highlight is, so you notice there's this block on the left-hand side, this little part of a sign or something. The higher order SVD sort of really pretty much doesn't capture that because it's not it makes sense. It's not really a big piece of the image. So if you're doing an SVD, you're not going to capture much information about it. Because we sample fibers randomly, essentially you see those appear in the fiber and Chidori pieces, and most likely it's because we sampled a whole fiber that contains or multiple fibers that actually contain that piece of the image. So even though maybe HOSVD might have slightly better error bounds, sometimes you can capture more salient information from the image by doing this fiber type sampling. Okay. So just to show some actual numbers associated with those pictures. So these are the 3 different data sets that I mentioned. They're sort of modest size tensors, order of 1,000 by 1,000, and then 33 spectral modes. And so what you're seeing here is the columns we sampled 60 fibers along each of the first 2 modes, which is not very much, and then 4, 5, or 7 of the spectral modes when we did it. And runtime wise, really the upshot is these are screaming fast because all I'm doing is just uniformly sampling fibers, and there's really not much to do there. So of course, it's very competitive in time with the HOSVD or even some other like faster variants of HOSVDs. So that's no surprise, but just to show you. But then if we sort of do a little bit of oversampling, and signal to noise ratio wise, the larger numbers are better here. We see that the Chidori decomposition does really well at sort of denoising the image in the compression. And interestingly, so the fiber decomposition, if you look up here, fiber decomposition is much faster because I'm just sort of independently sampling fibers and can do that like in parallel. But the Chidori version gives you a better signal to noise ratio in the reconstruction. So there's a trade-off there, just like there is in using the CUR as opposed to the SVD, that one is much faster, but maybe slightly worse on the reconstruction end. Okay, so I have, I guess, 10 minutes? Yeah, so let me just briefly talk about the matrix robust PCA problem and one way that you can use CUR decompositions for this. So here I'm going to assume I have a low rank data matrix and I have sparse noise. So the magnitude of the noise can be, or outliers really, I should say, can be arbitrary, but there are not very many of them. Okay, so here would be like an example of this. So I have images of this person's face, and maybe I have some occlusion that could be colored, could be not in certain spots. So during COVID, a mask could be a sparse signal. So if I have a bunch of images of the face and only some of them have that occlusion, as long as I have sort of enough of the person's face without that, the robust PCA problem is I want to uncover a low rank signal, which is just the person's face in roughly the same position. And then I want to recover the sparse outlier, which are those sort of occlusions or those patches that appear on the image. So you can also do this for videos, and I may show that in a moment. So the sort of natural formulation of the robust PCA problem is non-convex. So D is my noisy data matrix, L is my low rank part, S is my sparse part. So I want to minimize the error in so D minus L minus S. And I want to constrain that the rank of L is at most R, which is some fixed parameter that I know. And then that S has, some small portion of non-zero entries. So notation-wise here, I'm assuming I have an n by n matrix. So the alpha is the proportion of non-zeros in my sparse outliers. Okay, so this is non-convex. So Kenda's original proposal for the robust PCA problem was to do a convex relaxation. So nuclear norm of L plus L1 norm of S, relaxing the L0 norm constraint such that they add up to be D. Okay. Now this can be somewhat costly to run. And so I'm going to focus just on a non-convex iterative algorithm to approach this for the reason that we can do it really quickly. Okay. And so I promised you a definition of incoherence. So if I have the truncated SVD of L, and so I can define it on either side. I'll focus on the column side. So I take the left singular vectors of L, which I've called U here to confuse you between CUR decomposition. So I take the rth first CUR vectors. I look at the norms of their rows scaled by this factor n over R, and I take the maximum of that. So this can be either 1 on the lower end or all the way up to square root of n over R on the higher end. The low end is if I have a random Gaussian or a DFT matrix. The high end is if I have the identity matrix. And so we say a matrix is like incoherent or has small incoherence or good incoherence if it's closer to 1 than it is to square root of n over R. So that's something that you more or less need in order to solve the robust PCA problem. And that incoherence parameter is what's going to govern how much you sample to some extent. And then sparsity, we'll do it row and column wise. So for a tensor, it would be fiber wise, as opposed to proportion of the whole matrix, because I want to be able to sample columns And I don't want to get into an unlucky case where I had a really sparse outlier contamination, but it was concentrated in a column that I chose. So that's something that could really mess me up if I'm doing a column-based sampling approach. Okay, so here's the algorithm that I want to sort of highlight before I finish. So what I'm going to do is all I'm going to do in order to sort of try to reconstruct this low rank and the sparse component of my matrix is I'm going to assume that I've captured a good set of column indices once, and I'm only going to work with that column submatrix, and I'm going to do the same with the row submatrix. I'm basically going to clean up both of those, and then I'm going to do one CUR decomposition at the end to reconstruct my original low rank and sparse matrices. Okay, so I'm never going to view the rest of the matrix necessarily. Okay, so I fix a set of row and column indices, and I assume I've sampled incoherence R log n. I do an initialization where I just set my column and row guesses for the low rank part to be 0. And what I'm then going to do is do this iterative thing of low rank approximation and hard thresholding to capture L and S. So what I do is I take my noisy data, I subtract off the initial guess for the sparse noise, which is actually just 0. So basically my first step, I just take submatrices of D, I do a truncated SVD, and then I have this CUR approximation that is now an approximation of the low rank part. Then I take the column and row submatrices of my initial guess for the sparse outliers. The way I form those is I do a hard thresholding of D minus that low rank guess. So I keep large entries and I throw away small entries. And then I iterate. So I go back and forth between subtracting off the outlier matrices, doing a truncated doing a CUR decomposition, and then using that to add to my sparse outlier matrix. So I'm just alternating back and forth between those. And at the end, I return like one final CUR decomposition of L, and then I can get the sparse outliers just by subtraction. And so the real feature here is that a lot of other algorithms will or the one that this was inspired off of would do a truncated SVD at every iteration, or at least to initialize. Okay, and that's something that you don't really want to do because it's costly at all iterations. And so the complexity of this algorithm is n, basically rank squared n up to log factors in n. And previous to this, sort of the state of the art in non-convex algorithms was something like polynomial in R times n squared. Okay, so we go from quadratic in n to essentially linear. Okay. And just some implementation notes, we never actually form that product in the middle stage of the low rank guess because we don't have to. We just work with the columns and rows. And there is a variant of this where you resample columns and rows at every iteration to mitigate the fact that you could have made a bad sampling the first time. That's okay. The algorithm still runs. It's slightly slower, but you get a more sort of robust way of doing it. And then the tensor variation of the algorithm is more or less as described, just on the fibers. And this was done by some of my collaborators recently. And just to show you really, we compared with some accelerated alternating projections, which was one of Punch and Tsai and others' algorithms, which was kind of the current fastest at this time, and then a gradient descent-based method. And ours are drastically faster than that overall, and the reconstruction error is really, really good. And so to just finish up, sort of the takeaways that I want to highlight are, these are fast decompositions. They allow you to preserve sort of structure, and they're generally pretty good proxies for the SVD or higher order SVD or those type of methods. And you can produce a variety of algorithms that use this idea to denoise or solve a robust PCA problem or do matrix completion, tensor completion, only by viewing small subtensors or submatrices. And some of the theoretical results say you can often sample independently, although you may have to sample in a more sophisticated way if you don't have an incoherent tensor. So thanks, and I'll end there.